Well, hello everyone, and welcome back here to this example, the example related to a numerical example of fundamental power engineering. As you must be aware, we are working with this ideal transformer. We have been working for many weeks in the topic of the power transformer, the two-winding power transformer, and in particular, we are working with an ideal transformer. So today we have in front of us this very simple but very important and illustrative case of a numerical example of different loads conditions in this two-winding ideal transformer. So without further delay, let's start by reading this statement over here. Determine the active power output in kilowatt of a 5 kVA, 2500 volts, 120 ideal transformer serving loads with the following power factors. So the first one, as you can see over here, is a power factor 100%. In other words, the cosine of phi is 1.0. The second case, we are serving the load, but in this case is 80% the power factor, so the cosine is 0.8. And then we have a very ugly, very low power factor, 40%. In other words, is 0.4. And the final question, and it's a very interesting question, is to calculate the rate current, output current in this transformer. So every time that you are working with power, my dear students, the first step is you must remember this amazing and this very useful triangle. This is the power triangle. As you can see, this size is the magnitude of the apparent power. We have here the reactive power and P, the active power. The angle, the internal angle over here is what we call the power angle. So you must remember that using basic trigonometry, you can say that the cosine of the angle will be P divided by S. In other words, you can say P, it will be S, the apparent power, multiplied by the cosine of phi, or in other words, the power factor. So in this example, what we need to do is use this amazing equation over here to calculate the output active power. And to simplify the thing for my students, well, we will calculate here the power P2 in kilowatts, but using the kVA and the power factor. So now it's just a question. Of numerical substitutions. In the first case, we know that the power factor is the unity. We are talking about a resistive load. So we multiply the rate power, the rate apparent power of this transformer. You must remember the rate apparent power of this transformer is 5 kVA. We multiply 5 kVA by the power factor, in this case 1.0, and we obtain that for a unity power factor, we can use the maximum capacity of this transformer, and the output power will be 5 kilowatts. So we got here the answer for the question A. Then we want to calculate the output power, but now for the second condition, the condition B, the power factor is 0.8. So we multiply the 5 kVA by this low power factor of 0.8, and we obtain over here 4 kilowatts, okay? So as you can see, as the power factor reduces, the capacity of delivering active power is reduced, and in this case, we are talking about 4 kilowatts. finally, we have this very ugly power factor, 0.4. I say this is a very low power factor. However, we multiply 5 kVA multiplied by the power factor 0.4, and we got over here the numerical answer for the output power. In this case, this is the lowest of the three cases. This is only 2 kilowatts. Okay? So the final question is very exciting and very important, because when you are designing an installation for electrical transformer, it's quite important that you know the rate current. So in this case, they are asking for the output, and that means the secondary winding current. And to calculate that, what we need to remember, this is a single-phase transformer. In a single-phase transformer, the magnitude of the apparent power is the product of the secondary winding voltage and current. So from here, we can extract the current, and the current will be the apparent power divided by the magnitude of the voltage. Substituting the numbers, the rate power, 5 kVA, the secondary voltage, 120 volts, and voila, we obtain over here this amazing number for the magnitude on the secondary winding current. And as you can see, this is the current 41.6 amps, and that is the rate current at the secondary winding. So as you can see over here, if we are installing this transformer in any industrial process, in any machine, what we need to take into consideration is that the current will never go above this value, because this is the rate current. The rate current in the transformer is the current that the transformer can work forever without any damage, overheating, or negative affecting the life of the transformer. So that is the reason that this number over here is extremely important. So we are reaching the end of this video. I believe that all of you have worked today with this power transformer, 2-winding transformer. However, today we have a very exciting starting, because we are working with an ideal 2-winding transformer, and we were able to calculate the power transfer at different power factors, but also, and very important, the secondary rate current. Well, this is all for the video today. Thank you very much for watching, and I will see you at the next one. So it's time for, say, the classical bye now.